right, class? We'll get started. So today we're gonna have our YouTube Fridays exploring essentially Reynolds number today. We're gonna talk about what happens at extreme low Reynolds number and what happens at higher Reynolds number global perceived height flow. And we're gonna start to discuss what consequences that has for how we analyze what's going on in the first place. And I'm going to set us up for the discussion that we're going to have in the rest of the lecture today and on Wednesday, on Monday and Wednesday of next week, where we're going to be talking about turbulent flow. So we're going to kind of lay the foundation for that with some demonstrations today, including possibly my favorite demonstration in fluid mechanics of all time, because it's unmixing. Yeah. It's very turbulent. Trying for months now. Yeah, maybe it's a senior project I did. Out of order. It worked for the it worked for about a week, right? But you can actually hear the edits. Actually, you can hear the unsteadiness, which with characteristics of turbulence. All right, but we're going to start by discussing low Reynolds number flow. And just as a reminder, right, Reynolds number, how do we do Reynolds number? What is the formula of Reynolds number? Yes, so the numerator, velocity, diameter, and density, right? And in the denominator, we have viscosity, okay? So when Reynolds number is really low, which of those things is larger? Numerator and denominator, right? Basic math. So that means that viscosity or the viscous effects are really important when Reynolds number is low. And that's what we're going to see some consequences of in the first couple of videos, including that crazy unmixing thing. But before we get there, so this is a whole video on low Reynolds number flow. Again, it's longer than we have time to watch entirely in class, but I encourage you to watch the rest of it. And we're going to see a demonstration of essentially dropping liquid into a. So we're going to see so this is an example of dropping honey into a honey jar, right? Honey is very viscous. The Reynolds number here is very low, right? These viscous effects dominate over inertial effects. We're going to look at what happens if you do the same experiment and just like step up the viscosity as you go, and watch what happens to the smallest stream of fluid into light fluid as we decrease viscosity and therefore increase Reynolds number.
It doesn't give us any physical insight into the relative importance of viscosity and inertia. A similar experiments done with a control jet entering a quiescent mass of the same fluid can give us such an insight. In defining Reynolds number, the appropriate length and velocity to be used are the diameter and the velocity of the jet as it enters the fluid.
So again, it's simple stuff. So this is like, and this is honey being dropped into honey, but the honey being dropped in doesn't die at right? Visualize this happen. And now the narrator just said that the Reynolds number, we're going to compute Reynolds number of this jet, the diameter of the jet, times the velocity, times density over viscosity. And so we're going to see Reynolds number computed for a couple of situations here. And this jet, because it's falling, right, being dropped from some height, has some velocity, this fluid has mass, therefore it has momentum as it enters the tank. Right, the jet has momentum as it enters the tank. Then upon entering the tank, it encounters resistance because of viscosity. Right? So the viscosity of the fluid within the tank slows it down and will then stop this jet from going any further. So that's what we're seeing here. In this case, the viscosity is so high, the Reynolds number is so low, the jet basically doesn't go anywhere. Right? And what we're seeing here is just this like diffusive spreading of that dyed honey at the top. The jet is the influence of inertia is so low that it basically stops moving as soon as it hits the back of the fluid. Viscosity is so high, it's very, very low level. Now we're going to see what happens if you go to lower viscosity and therefore higher Reynolds number.
Here the fluid is syrup, and the Reynolds number is 0.05. At this low Reynolds number, the jet hardly penetrates at all. Now let's repeat the experiment using different fluids. The other three boxes contain glycerine, and water, and water. Each jet will be driven by this piston, and the velocities will be identical. This glycerine jet penetrates to a depth of a few diameters. At this Reynolds number, the jet penetrates many diameters. The tangential force acting on the outer surface of the jet is insufficient to reduce the velocity very much.
The tangential force acting on the outside of the jet is viscosity, right? That's the viscous force. In this case, we have a Reynolds number of 200, being an inertia. It's now substantially more important than it was in that Reynolds number of 0.05 case. You see that the jet is actually falling, right? The inertia is overcoming that distance drag, and this fluid is falling quite a far distance, right? We're not yet turbulent, right? We don't have turbulent mixing at the edges of the jet, but we are, but inertia is still important.
Before it reaches the bottom of the box. This jet becomes turbulent.
So now we have turbulence, right? So now we're at Reynolds number above 2000, which is going to be the kind of Reynolds number jet. And you can see, right, that first of all, just like in that Reynolds number 200 case, the influence of inertia is definitely much larger than that of viscosity because the jet penetrates right deeper into the fluid. But then in this case, the Reynolds number is so high that it also transitions to turbulence. And in that turbulent flow, we have vortices that are being created that are shedding into other vortices, and smaller vortices, and smaller vortices still. You can see that kind of characteristic roughness, right, of the edge of this jet. That indicates that we have vorticity or vortices on both scale. That is much higher.
Here, for comparison, are the four situations.
So Reynolds number, what we've learned here, what we've reviewed here, is that Reynolds number is the ratio of inertial forces to viscous forces. Inertial influence to viscous forces. Plays a really important role in determining what happens in our flow. Again, don't know the Reynolds number, you don't know much about it. So we're going to look at some consequences of Reynolds number being down here in the next two demonstrations. So we're going to look at Reynolds number, ultra low Reynolds number. We're going to take Reynolds number much less than 1. So we'll say, we typically write this. We'll see it written in the next video this way. So write it as RE much less than 1, which means it's like double less than sign, meaning it has much less than 1. In practice, this is RE less than about 0.1. What we mean by double less than. And we're going to look at the consequences of Reynolds number much less than 1. And note that here, right, this is Reynolds number 200. This is still laminar, right? So all of these are laminar. But this, you see the second demonstration, the presenter is very enthusiastic for this ultra laminar flow. We would call it creeping flow or Stokes flow. Is what this is over here. So we're around much less than 1. So it's laminar. You share some characteristics of ordinary Latimer flow, we were going to see Latimer flow. But there are some other strange properties that we're going to see when the flow gets to slow down. Yeah, it's a very wide, like swirling as it's dropping, but maybe it'll go around with the video. Oh, I think this is swirling when it's dropping because essentially the jet that you dropped in is not getting out of its own way. Imagine if you drop money in, right? It kind of swirls up. Kind of swirl on the top. Because there's, again, momentum is not important at all. So the stuff you're dropping in is not moving out of the way, right? It's actually, I said this with confusion. I think this is really actually just the weight of the jet that you're dropping in, pushing the other jet fluid out of the way. All right, so we're going to watch one iteration or one demonstration of my favorite experiment.
Low Reynolds number flows are reversible when the direction of motion of the boundaries which gave rise to the flow is reversed. This may lead to some surprising situations, which might almost make one believe that the fluid has a memory of its own. Here are two concentric cylinders. The fluid can be moved by turning the inner cylinder with this handle. The annulus between them is filled with glycerine. Into this space, I introduce some dye, which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea.
Just think about what happens if you drop, these devils drop a milk into a cup of tea or something into a cup of water, right? If you do that and give it, 1, 2, 3, 4 stirs, it's the flow that you're creating is like turbulent. The Reynolds number is high enough that you create a turbulent flow, but when you stir it around. Inertia is important. Right, and you end up with turbulent mixing. So if you stir backwards in the other direction, you don't get back that drop, right? But we'll see that when inertia is effectively 0, right? Reynolds number much less than 1 implies that the influence of inertia is effectively 0. Right, it's all viscosity. Then we can see, we'll see what happens.
Now I reverse the direction. And after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion.
Same. Okay, absolutely the same. But that's essentially because of the fact that inertia plays no role in this flow. Reynolds number is so low that inertia plays no role in this flow. So inertia would mean that, like, when we turn this inner cylinder, if inertia played a role, Reynolds number were higher, then the fluid containing this dye, the fluid all around it is moving a little bit, even after you stop spinning that inner cylinder. And then when you try to undo it, when you try to unwind it, you would never be able to unwind it the exact right amount. And every time you start it and stop a little bit, the fluid will keep moving just a little bit. If the Reynolds number got even higher, you have turbulent mixing. This thing would mix really well, really quickly. But because essentially there's no inertia and Reynolds number is super, super low, you can do this. Right? As you turn the inner cylinder, as soon as the preventer stopped turning, it would instantly stop. No inertia. And so they're able to do this trick. We're going to watch another demonstration of it that is in full color and high definition with a very enthusiastic presenter. I think a better demonstration will give you a better idea of what's really going on with this, which different camera views of what's happening.
It is laminar flow day, and you know this about me, I love laminar flow. There's a cool video on Smarter Every Day that talks about how laminar flow works, but we're doing what I call today ultra laminar flow. It's not really called that, I just made it sound to try to make it a thing, but
Creeping flow or so slow, but we really want. But ultra laminar flow. Okay.
check this out. We're gonna look at something called Taylor Couette flow. My man here, Maurice Couette, French guy, he came up with a device so that you could quantify the viscosity of a fluid by a cylinder rotating on the inside of another cylinder. It's really cool work. My dude here,
Do you think the viscometer lab? Yeah, so this is a different type of viscometer. Right, so you're doing a viscometer of a rolling ball.
No, the calculator is.
The calculator.
I have it.
Yeah, so this is a different type of, so essentially this device that we've seen is a spinning, rotation of the inner cylinder inside the outer cylinder. That's another type of viscometer. Viscometer being a weight measured viscosity of fluid. In this case, if we measure the force required, to spin that inner cylinder, you can figure out what the viscosity of the fluid was. And then this, you've got to introduce Taylor. Taylor, our old friend from scaling, right, the atomic bomb estimation thing. Same guy, did a lot of good mechanics.
Sir Taylor, he expanded on Couette's work and he measured stability inside Couette flow. So you combine the two, you get Taylor Couette flow. What we're gonna look at today, if it works. I really want this to work and I want to do this experiment for a long time. We're gonna look at ultra low Reynolds numbers flow and hopefully we get reversible flow. Let's do this. First things first, we've got to fill up the tank with this corn syrup, which is a very viscous fluid. Here we go. It's going to take quite a while. This is a lot of corn syrup. Liquid overflow effect. We should revisit that. That's the topic for another video. Okay, here's the magic of Taylor Couette flow. We have something called a no-slip boundary condition. So on this inner cylinder here, the corn syrup wants to stick to it. And on the outer cylinder, it also wants to stick there. So if I'm rotating that inner cylinder, what's happening is it will try to move along with it. So if we were to draw a line across the gap there, and we were to rotate it, the inner cylinder would pull along the inner corn syrup, and the outer corn syrup would stay there. And so what would happen is you would create this spiral pattern. In fact, if you look down through there, you can kind of see it happening in the clear fluid. So what we're going to do is we're going to put this colored corn syrup in there, and because we have such a low Reynolds number here, that's laminar flow, and it should be reversible. Okay, so as I put this color in here, I want to recommend something. What you're about to see is absolutely incredible, and you're only going to get to unwrap this present once. So if you would, please trust me and don't fast forward this video. In order to fully appreciate what you're about to see, you need to watch it unfold in real time. Okay, here we go. We're going to go for 7 rotations. Everything I've seen on the internet does 5. And go. So you should see the spiral start to happen.
See exactly what you illustrated about no slip condition and flow, right? Look at that red spiral. See that the outer edge of it is basically not moving from the original wall that it was close to. And the inner edge of it, we continue around here, continue on a spiral that would be this inner wall with no slip condition and the wall. You can see that it's not moving this thing perfectly smoothly. So every now and then we'll stop a little bit, flow perfectly smooth. Yeah. We're so low that there is effectively no difference.
1.
Try to move it really slow, but it shouldn't actually matter. You can start and stop. Because again, energy doesn't have to
See the spiral.
right? So you start and stop, you go backwards a little bit, and you just get this thing back.
Three. Is your heart pounding? Can you see the spiral then? Or it's like making candy cane looking things. I don't think it's linear. But I think the gradient of the flow across the entire thing. Is it 6? It's 6, I don't know. Got so excited. Oh, dude. Look at that. It's like a marble. Can you see it? Focus further down there. 7. Okay, here we go. 7. It looks like it's completely just all mixed up. Oh, man, it looks like you can never get that back together. Okay, here we go. This should work. Reversible flow, ultra laminar flow, Taylor Couette. Let's see what you got, boys. Ready? Here we go. I'm nervous it's not gonna work. Oh, gosh.
Slow down.
You should have 4 smiles after this. I've lost count because I'm so excited. I think it's coming up on 5. That's 5. Let's get in there tight. It's about to start getting crazy. We have 2 more. Come on, baby. I'm so worried that the red and the blue are going to mix because they were very, very close to each other. Like radially. 6. Okay. This should be it. Please work. I want you to work so bad. Is it working? Did it work? Yes.
Here's you watch the rest of the video, it'll be great. We get to watch, so okay. So this kind of, it's called kinematic reversibility. This is the consequence, the important concept here is the consequence of ground number being so low and for the influence of inertia not being important in this manner. And so we can reverse, right? Our flows are therefore time reversible at ultra low. Yeah, so okay, one thing I wanted to ask you, so it doesn't matter if you stop and start a little bit, right? You're trying to run very, very smoothly. It doesn't really matter if you stop and start because inertia doesn't matter. It doesn't matter how fast you spin. Yeah, why? Exactly. Right. So if you spun too fast, I think the viscosity here is so high, I might require more power than it's realized. But if it's spun too fast, then the rotor might become high enough that you no longer have this whole. Yeah.
So theoretically, we're turning the speed of turning. If you did this with water, but like a ridiculously low speed, would it still work?
It should still work with water. I would say you would also need an incredibly low light. You have to really. Because so in theory, yes, it should work. It's just go very, 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 very slow. But there's likely to be thermal gradients and other things that will cause disruption with the water. What do they call it? Water. So, but those are 2 separate things, right? So the molecular diffusion of the dye, yes, definitely, the diffusivity of the dye in water would be higher than in this serum, right? And you can see the effect of diffusion, right? So this thing started out as a nice little uniform blob, but it's kind of spread out a little bit, not because of mixing, not because of fluid mixing, vacuum mixing, but because of diffusion molecule. And that effect would be much, much larger in water, because molecular diffusivity is higher in water, right? But in theory, in this incredibly, incredibly slowly, and there was nothing else causing the fluid to move, then it should work with water. My guess is practice you couldn't make it work on a slight scale because like a small temperature gradient across the device or small jostling of the table right, would cause small vibration. That would be enough, to cause other those things, right, but yeah, in theory, at very, very low runoff, in water, the same thing would happen. And actually, similar things, we'll look at, saving this for another class, we will look at, the effects of ultra low Reynolds number in water, and the impact that that has on life, the impact that that has on how cells experience the world, how cells swim, and that's in water, where when the size, in that case, the size is so low, but the Reynolds number is really tiny, and you can see similar kind of reversibility, and that has implications for how like bacteria swim. So it can happen in water. My guess is incredibly important. Does that make it easier if you like cool down the water super cold and just increase the pressure? That might have some. So the molecular so yeah, so if you were to do some water, molecular lucidity would be higher. This thing would spread out more. If you did it incredibly slowly, there were no other oscillations, right? Then it would still come back to be a bigger spot. Okay. I'm not sure about the impact of doing this incredibly slowly. I think we would have to do this very small. Yeah.
Like how close to them it's supposed to be.
Stops really. Yeah. Yeah. Sorry, go on.
It's not.
So turbulence creates more activity, that's correct. Because it's mixing more effectively. In this case, I mean, we are increasing in entropy, right, because of molecular diffusion here. It's just that because the flow is time reversible, the flow itself is time reversible. We have cinematic reversibility, but there is no effect of inertia in this flow. We're actually not increasing the entropy because of flow. We're not increasing the entropy because of flow itself. There's going to be some. There's definitely going to be some, right? So there's diffusion, right? Russell generates a heat units. But yeah, that's what. But I don't fully. Other questions? Okay. Yes, we're not violating current acts here, but we are. Okay. So we are, however, going to be talking about turbulence, and this concept of mixing is actually incredibly important for understanding what's happening within turbulent flow. So for understanding what we're going to see through the math that we'll be doing starting today, continuing through the next couple of class periods, we need to talk about mixing in turbulent flow and the impact that that has. And an important concept that we're going to see here is something about mixing of momentum. We're talking about mixing of dye, but we're going to talk about mixing of momentum, and it has a really important role in turbulence.
Prominent in our defining syndrome was the word mixing. What about mixing? Let's modify our experiment by introducing a thin.
I want to say, we're cutting in the middle of this video here. This video is talking about turbulence now. Essentially defining turbulence as having these kinds of different characteristics. One of those important characteristics is not really the consequence that we're looking at here today.
Streamer of dye into the flow. Notice that the dye forms a thin film, maintains its identity with very little change right down the tube. The only mixing is molecular, and the concentration gradient is so small that this process is very slow.
It's laminar flow in a tube. Reynolds number is maybe 100 or so. Just guessing based on what so on, etc. is slow. So Reynolds laminar flow in a tube. This is the same demonstrated we saw images of in class the other day. We have dye introduced in the central stream, and now we can see that it maintains this nice smooth line right all the way down to the end of the pipe. You can see what's happening here at the outlet of the pipe. We can actually understand this now if we know the velocity profile, right? The velocity profile is parabolic. So the flow in the center of the pipe is traveling faster than the flow at the edges, right? The center is traveling faster than the flow at the walls. That fluid at the center has higher momentum than the fluid at near the walls, where there's no slip conditions. And therefore that fluid with higher momentum travels further out the center of the pipe than the fluid at the walls. Right, the fluid at the walls is slower, so it falls faster. You can actually see something about the velocity profile by looking at the outlet of the pipe.
This is laminar flow. Now we increase the Reynolds number. At the onset of turbulence, our diaphragm seems to explode, and the dye is rapidly mixed across the tube. If we want to, we can regard the increase in pressure difference as a manifestation of mixing too. Mixing of momentum.
Watch on this bottom right, you can see that this outlet flow is changing, kind of oscillating between two different states. We're talking about what looks like a turbulent state. That indicates that they're right at transition. This is right at transition around the curve. Where they're running this thing right now.
In laminar pipe flow, the velocity profile is parabolic. Near the wall, there is a considerable quantity of relatively slowly moving fluid. Dye, injected near the wall, parts from slowly moving fluid. When it leaves the pipe, it falls with a steep trajectory.
To inject the dye here in the wall.
Notice that the slowly moving fluid near the top of the pipe also falls steeply. The rapidly moving fluid from the middle of the tube falls with a flat trajectory.
So this is that back from the fluids.
Compared with laminar flow, in turbulent flow, the mixing of momentum causes the velocity to be much more nearly uniform.
So this velocity profile, we developed the velocity profile for laminar flow. It's going to be a major task of our work. Today, Monday, it's going to be to derive the velocity profile for turbulent flow. And we will see that it is much flatter than the velocity profile for laminar. In fact, it's generally you're going to see flatter than this, meaning that it's more uniform velocity across the center of the pipe that we see in laminar flow.
The fastest fluid is not quite so fast, and there is very little slowly moving fluid. What little there is can be dragged along with the rest and it leaves the pipe. Nevertheless, the velocity must vanish at the wall, so we can regard the wall as a sink for momentum. Turbulence increases the rate at which momentum is transferred toward the wall. Thus, the turbulence. We need a larger pressure gradient to replace the momentum lost to the wall.
Stop for a second. And the last bit of video segment. Something the narrator just said. That we can think of the wall as a sink for momentum. We have no slope condition, velocity is 0 at the wall, momentum goes to 0 at the wall. Where the momentum is high in the center of the pipe. And one effect of turbulence mixing, right? So we put the dye in here, the dye mixes really nicely uniformly across. We saw it, the dye mixed really uniformly across the whole pipe. But that mixing also occurs through momentum. The momentum of the fluid mixes because of turbulence. And that tends to even out, that is what's evening out the velocity profile of turbulence. It's the mixing of momentum in turbulence that causes this velocity profile to be pretty flat and uniform across the pipe. So turbulence mixes the flow. It makes dye. We've seen that. It also makes momentum. And that mixing of momentum is what's going to drive this velocity profile. Okay. Now I see a lot of confused faces. for free space. Any questions on that concept of Dixon? We'll see, we're gonna see the map. And we'll see where that comes from. But the quarter mile for Jeff. So this velocity profile. Yeah, that's a very good, very good question. Yeah, so this is the time average velocity profile, right? So if we were looking at the instantaneous velocity profile, we would see all kinds of all kinds of fluctuations. Yeah, I automatically assumed that. Yeah, but I was. Yeah, so this is that U bar, right? It's actually what the bar here. Yeah, it's but yeah, so this is U bar. We're not visualizing here the time average, the fluctuation of velocity profile, time average.
That's why this also doesn't have any vertical.
Yes, that's why there's no vertical velocity shown here, because in this case, if we're assuming the flow is all the way down the pipe, the only time average component that's non-zero, and the P, W, time average component is zero, the fluctuating component. Yeah, great. Yep. So this we actually understand, we only understand on the basis of rental data. And again, when we're analyzing pipe flow or an engineering situation, we really just care about the average. We generally just care about the time average velocity. And so our major task is going to be trying to figure out what this velocity profile is, and therefore what the friction factor looks like for pipe flow, for turbulent pipe. It's going to be different from software. All right, any other questions? Okay. We're back into it. So, so most of the time, all we care about is the average, time average solution to the flow, right? Most of the time, all we care about in pipe flow is that time average velocity profile. That is all predicting what that is within the so we have this concept of Reynolds averaging, right? Where we're going to split this would be an instantaneous velocity U at some given point. Let's say that turbulent jet. We're going to split it into a time average component U bar and a fluctuating component U prime. We're going to try to develop a set of equations that Jeff told us about U prime. U bar. That's really what we care about. And so we're going to take each variable, right? We can run over this in class the day, but we're going to take each variable and split it into its time average fluctuating components and an average of fluctuating components, and plug that into Navier-Stokes. We're going to get a new set of equations, a new time average Navier-Stokes equations. So the result was the RANS equation, Reynolds average Navier-Stokes equation. Fundamental to how we simulate turbulence. Right, so in a computer, CFD, we use RANS, the RANS equation all the time, right, to model the turbulent flow. And we take that Reynolds averaging operator and we apply it to all the variables, the velocities and pressures within our Navier-Stokes equations. Well, we end up with, we're not going to go through that derivation here, but we're going to look at the resulting equations. For continuity, we end up with this expression. So this is du bar dx plus the v bar dy plus the w bar dc is equal to 0. This looks exactly like continuity for just the full velocity. We just replaced all the velocity terms by the time average instead of the total velocity. So in continuity, all the fluctuating stuff, all those u primes, v primes, w primes, all dropped out. This is great. This is our goal. Okay. In doing this Reynolds averaging, our goal is to write a set of equations that only have these time average quantities. So this works. Okay, this is what we want. This was our goal. Doesn't work this way for momentum. Momentum. This is the momentum time average. Sorry, Reynolds average momentum equation. In the x direction, right, remember we have three of these, one for x, one for y, one for z. And if we start over here from the left, it looks pretty good. Total derivative of u bar with respect to t. Good for one, right? We only care about u bar, v bar, and no v bar. We only care about time average. That's all that's here. Good. dp bar dx, great. Time average pressure for one. Rho gx, gravity is not fluctuating, turbulence, so that's fine. Edx mu du bar dx, great. Minus rho u prime squared. That's a problem. But that's something we have to deal with. dy mu du bar dy plus this term. Rho u prime d prime. The mean of rho u prime d prime. Same thing. We have another fluctuating component now. So our Reynolds averaging operation resulted in a set of equations in terms of our average velocities and pressures, as well as this is like the time average of something about fluctuating. Okay. These pieces here are what make turbulent modeling, what the turbulent model is all about, trying to figure out what's trying to approximate what these things are. Is what we do with turbulence models. Because if we can figure out what these things are, or like what the value of these things, these fluctuating components are, then we can use this set of equations to simulate the time average velocity profile. So these things here, call these the turbulent stresses. Okay. These terms here, rho u prime squared, mean, rho times the mean of u prime squared, rho times the mean of u prime d prime, rho times the mean of u prime w prime, these describe the influence of turbulence on the mean flow. What we care about is u bar, right? And these terms here tell us how the turbulent velocity fluctuations, right? All the fluctuating components of x and y and z velocity turbulence, how those things influence the mean flow, how those things feedback and affect the mean flow. This is why the velocity profile, turbulent flow in a pipe, just saw in the video, going to be different from the velocity profile for laminar flow. Influence of these things that drive it. So we'll talk a little bit more about these terms, but want to note we ran into equations. This set of equations, they're very commonly used for turbulent flow, for simulating turbulent flow, in computational fluid dynamics. So when you do your CFD tutorials and projects, you see the RAND equations, and you may be using the RAND equation depending on the problem you're solving. And you're going to see it as an option in the answer code. It's a standard way of handling turbulence. We also can use it for semi-empirical turbulence models. That's where we're going. We're going to develop a set of a model of turbulence, look at a model of turbulence that allows us to predict what's happening within tight flow. So we care about this chapter. And will be based on these. So the note on turbulent fluctuations, okay, those turbulent stresses. From our definition of that mean operator, that overbar averaging, time averaging operator, we just looked at what the average of, let's say, u prime, time average fluctuating component of velocity. It has to be zero, right? Because we split our velocity into, say, u was u bar plus u prime, right? Where u bar is the time average. So that means that the average of whatever's left over, the fluctuations, has to be zero. Average of u prime has to be zero. But you'll notice from our equation, we have something like u prime squared mean. Looking at the time average of U prime squared. This thing is not general state. So, and nor are the other mean fluctuation problems. So one way that I think about this is let's look at two signals, let's look at F and G. F is sine of T, and G is sine of T plus 45 degrees. So the time average of a sine function is just 0. Right, so the time average of F is 0. Right, F bar is 0. Time average of G, also 0. But if I take F times G and do the time average, I get a line, and this line is at about 0.25. It's not 0. So if I take two things, right, if I'm taking these two functions, time average of both of them is 0 on their own. Now, if I multiply them together, then take the time average. The order of operation matters. Okay, multiply them together first, then take the time average. I end up with something that is non-zero as the average for 0, which will 0 down. So the time average of these things is non-zero. Similar thing is happening here with our fluctuation. Time average is non-zero. The time average of P prime multiplied together is non-zero. Time average of P prime squared. Yes. So the time average of fluctuating velocity component, velocity is 0. Over there.
Because we said so.
Because of the definition, okay? Because we define our velocity as having a mean component, and then everything that's left we said was the fluctuating component, the prime component. And so the time average of everything that's left has to be 0. Okay, our definition of what that average is. But now let's look at this one. Maybe let's start here. Okay, if we take U prime on its own, take the time average, and put a bar over U prime itself, just itself, we end up with 0. Right? D prime, the average of just D prime itself, we get 0. So we multiply the two together, then take the average. Okay. And one way to think about it, one way I'm trying to give you some reason to believe that, okay, is through this example here. So it's not what we're trying to do. Let's imagine for a second. So this is F, say it's D prime, and G is D prime. F is sine. Time average of sine, the sine function, 0. So F over bar is 0. G is also a sine function. I just shifted it over. Phase shifted it by 45 degrees. Time average of this is still 0. Okay. But now if I multiply F times G, then take the time average, non-zero. Okay, and that's what I'm throwing down here. So F times G, so this line down here is actually 0. If it's bigger. This line down here is actually 0. See that F times G, because it's one is is oscillating about some other point that's non-zero, some other line that's non-zero. So if I take the time average of F times G, I get something that's non-zero. Okay, so I'm just trying to show you that it's possible to have two functions that both have time average of 0. When you take the product and then time average, you get something that's not.
So order of operations wise, we're taking the time average to the very max.
Yes.
That's what it's.
Yes. So this is saying it's the time average of U prime times V prime. Okay. If we did time average of U prime, time average of V prime, we have 0. But we're doing this class. Time average class. Yeah.
So is it the time average of the individual component is 0 because it might oscillate around 0?
where zero is basically the average point. Zero is the average point. So remember, we said that we have u versus t, we have some velocity, that's our u. We said that this is u bar, right? The average of this, time average of this is u bar. So what's left, right? All of these pieces is u prime. Right? And so the time average of u prime has to be zero. But if I multiply it by itself, or by another one of the fluctuating velocity, then take the average. That is non-zero.
Is it always not zero or we see it's very, very close?
Turbulent flow is always turbulent flow is always zero. And this is we're gonna end here. But this is critical, right? This tells us that these things cannot be ignored. If we would love to ignore these, we could ignore these terms. We would have a Navier-Stokes equation, a set of Navier-Stokes equations that are only in terms of the average velocity. All we care about is ignore all the terms. But because these things are non-zero, we cannot ignore them. They play a role in determining flow, and we're going to have to deal with it. All right. Thank you all.